Take-home message. Scientists think that aerial backpropagation is not biologically plausible due to weight transport, backward locking, and local updates problem. Previous work proposes feedback alignment and targets propagation to mitigate these issues. In this work, we present countercurrent learning, an even simpler and more efficient version of target propagation algorithm while achieving comparable results. Today, we will consider a simple single-layer MLP network. We offer the aerial backpropagation derivation for your reference. A central question regarding backpropagation is credit assignments, which means how to assign credits and penalty to individual neuron. The first sub-question is, who backpropagates the errors to the responsible neurons? Basically, neurons transmit information unidirectionally. The same neuron does not transfer information in the opposite direction. The researcher proposes that there is another feedback network that transmits information. For example, there should be a feedback network. However, should the forward and feedback network share the same weights? If yes, then we need yet another mechanism for instant synchronization between the feedback and forward weights, which is not yet discovered, and it is considered the weight transport problem. Another problem is the backward locking problem. This means that the forward network cannot accept any inputs until the feedback network or the aerial backpropagation is done. A biologically plausible alternative to backpropagation is the target propagation family. The ideal output target is T, derived from target minus the arrow. Target propagation then reconstructs ideal targets for different layers in a backward manner. For example, it reconstructs N using M, H, and I. For the loss computation, it solves the loss between H and N by updating B3, and the loss between I and M by updating W3. Can we make target propagation even simpler? The answer is yes. We get inspiration from countercurrent flow heat exchange mechanism from both engineering and biology. Instead of using ideal targets, we use ground truth labels to begin the target propagation in the feedback network. Then we solve layer-wise loss by updating B3 and W3, over the loss between H and N by updating B3 and W2, and likewise. As you may observe, the feedback network is independent from the forward network. Theoretically, it is faster than backpropagation. The result shows that countercurrent learning algorithms achieve comparable results with feedback alignment and target propagation algorithms. We show that CCL is much more efficient than target propagation algorithms. It is faster than DRL by 30 folds and FWTDP for 6 folds. We also show that countercurrent learning is able to be applied on autoencoding tasks. In terms of visualization of convolutional kernels, we can see that backpropagation contains more high-frequency components, while CCL does not. We also show the results on different learning rates. Here we show some examples of the countercurrent system in biology, for example, for oxygen exchange, or for keeping our core temperature high. Thank you for your attention.